to talk about how to solve the Scholes equation with an ion trap. So first of all, let me introduce you the equation. In particular, we want to solve a partial differential equation. It is a parabolic equation and it is also backwards in time because the sign of the time is reversed with the typical equation. And also we have to add a contour problem, which will be the payoff condition. In this case, we are assuming the easiest problem of pricing option. So we have this linear function for the payoff and 0 in case that the stock is under the strike price. So this equation depends on a lot of constants, which are related with the market behavior. So just assume them as constant and as constants. And the point here is that we have to solve a contour problem through quantum simulation techniques. We have already solved this problem using a digital quantum computer, using quantum gates, and now we are solving this problem using an analog device. So let me reformulate this problem as a Schrodinger equation. So basically, we can split the partial derivative with respect to time and obtain a Hamiltonian. And this Scholes Hamiltonian has two parts. One of them is emission, and the other one is not emission. So this means the main issue in order to reproduce the dynamics of the partial differential equation in order to obtain a solution. So the trick that you may already know, it is to embed the propagator instead of the Hamiltonian. So we can embed the term propagator of the non-emission part with a technique which is called as unitary dilation. So by using one single ancillary qubit, we can introduce this ancilla and hence obtain an antenna which can be expressed as an exponential of a sigma y operator plus a pseudo Hamiltonian that it's the cosine of the propagator that was not emission. So now the point is that once that we evolve our system, because we have a large space, this subspace is going to lose probability that is going to be transferred to this subspace of the ancillary qubit, and therefore we have that the desired dynamics corresponding to the non-unitary operator is going to be related with the zero state of the ancillary qubit. So if we want to reproduce these dynamics by using a physical system, we need to be able to implement both the spin operator sigma y and the momentum operator, which is the one that is present in the Hamiltonian oscillation. So the proposed physical system to reproduce these dynamics, this is a trap ion. So imagine that we have two trap ions. So we're going to introduce three lasers. The third of them is just going to be directed to the first ion, and we also have two more lasers that are not necessarily so much precise, so they can point to both ions at the same time. So just to remind you, we have in this case this ion trap two irrational modes. We'll have the first one, which will correspond to this movement, and the second one that corresponds to this of the movement of the ions. Because of the difference of frequencies, we can ignore the second irrational mode. So essentially, the Hilbert space in which we will be solving our problem will couple the spin with the first irrational mode, and we will have a state that will have the embedding part corresponding to the spin of the first ion, the second spin that we will use to measure and retrieve the information, as we will see later, and we also have the bosonic part in which we will encode the solution of our problem and operate with the momentum operator. So how we encode The bosonic part, we can interpret this as an harmonic oscillator. So basically we have an orthogonal basis, and this orthogonal basis is given by the wave functions. And if we have any, by the harmonic wave functions, so if we have any wave function, in particular the one that is encoding the initial condition of our problem, which is basically a wave function that corresponds to normalize this, carry to next space. So it's something like this and duplicate. So if we normalize this is the wave functions that we want to introduce as the polynomials at a base. We can calculate the coefficients and express it into the base. So in principle, this base will have an infinite number of terms, so we have to cut down somewhere. So we decide which is going to be the number of terms that we are going to consider with respect to the similarity, the self-fidelity that we want to reproduce the initial condition that we want to load. So I'm showing you some results. We are solving a reconstruction up to a certain number of terms, a certain number of harmonic terms, and the target function that we want to load. So if we use only the first harmonic, the first focus state, this will be the approximation that we will have. And as we increase the number of terms, we achieve a more accurate loading of the initial condition. So by using 14 harmonic terms, we have a similarity measure of 0.9975. So this is going to be the choice for loading the information into the electrode. So we are going to use the first 15 focus states from 0 to 14 to load the information. So once that we have seen how to load the initial condition of the boundary problem, we need to know how we can do it experimentally, because it is quite complex and manipulate more than a few focus states. It's quite difficult with respect to the experimental implementation. So this is the point. We want to load a state which depends on the first 15 focus states. So we have this protocol which guarantees fidelity over 0.9 for the first 4 or 5 focus states. And basically the trick is as follows. So let's start with the ground state in both the spins and the bosonic part. So now we have two lasers with two certain frequencies and Hamiltonian and the corresponding Hamiltonian. So by choosing the Rayleigh frequency and the phase of both lasers, it is possible to achieve the transitions that connect the ground state with the first, let's say, it's quite, the quality is not quite good, but the excited state, so we transfer certain probability from the ground state to the excited state. And once that we have done this by the first time, by introducing two other lasers, changing the Rayleigh frequencies with the start shifts, we can achieve all the transition connecting the ground state of the spins with any other excited state of the spins with the corresponding bosonic excitation by choosing the Rayleigh frequency and the phase of the lasers. So we can carry probabilities from the ground state to each of the excited states. So the problem here is the accuracy, which you can choose all the parameters of the physical devices, so you have some imperfections that will limit the protocol. So now that we have loaded information, we need to perform the dynamics. So basically, the black Scholes Hamiltonian will act on this state that has both zeros for the spin state and the initial condition loaded in the bosonic part. And we have two Hamiltonians, the emission, which is quite easy and straightforward to be implemented, and the non-emission part that we will approximate per some pseudo time with the momentum and some pseudo time with the identity. So we are looking for this expression to implement the dynamics of our system. So the point here is that these two are the desired Hamiltonians, and now we have to obtain all these terms for the spin and bosonic part with the two lasers Hamiltonian. So basically, this is like a trivial example when we have two lasers acting on the first ion. If we go through an interaction vector, we assume that we can apply the landing regime, and we perform a rotating wave approximation, considering that the arriving frequency it is much smaller than the frequency of the trap. We can achieve this Hamiltonian, and choosing the tunings and traces of the laser with the next coming and the next coming transitions, it is possible to obtain Hamiltonians of this form, where we can obtain the same terms that we have in the desired dynamics. So this is the trick, and now we have to simulate this. So the point here it is that in this case, let me go. Sorry. In this case, as you may notice, here we obtain a sigma wave, and we have an identity in this case for the momentum, and it is not possible to obtain both identities for the two spin parts. So the trick here it is to initialize our state with the second spin in the ground state of the y sigma y. So once that we have done this, it's time to perform the dynamics. So first of all, we have simulated the space, which is the space of the stocks, and we also have a real space, which is the physical one of the ion trap. So we need to scale our operators from the reality, the physical operators, to the simulated operators that are describing the dynamics of the market. So essentially, for the first and second Hamiltonian, for these two terms, we are going to use laser 1 and 2 that are acting on both ions at the same time. So basically, we will evolve from time 0, and let's suppose that the time of the first Hamiltonian acting on the system it is smaller than the time of the second Hamiltonian acting on the second one. And basically, we evolve our system with these two lasers till this time, and then we apply a pi pulse which will allow us to revert time somehow on this period till the end of time. So eventually we will obtain the evolution according to these two Hamiltonian, and finally we will evolve this driving, just acting on one of the two ions, that will complete the entire dynamics of black zones. We will consider a thermal noise in the evolution that will correspond to this Javier, and basically because of the spontaneous production of bosons has a time quite larger than the evolution times, we are not going to suffer from noise. So the solutions that we obtain by simulating these dynamics are the following. So here in red we have the black source initial condition. I just plotted it because I wanted to make sure that we have enough dynamics that the final state is quite different from the original one. So in green we have the exact solution obtained by the analytical form of the black solution, and in blue we'll have the desired dynamics corresponding to the Hamiltonians that we want to implement, but actually because we are performing some approximations of the Hamiltonians of the trivial, we have that the real quantum dynamics, it is a little bit different corresponding to the Saga dynamics that we would like to obtain, and basically the fidelity between these two plots, it is 0.9866, which provides a more than satisfying result, but nevertheless we still have to find a similarity between the real implementations and the exact dynamics, because maybe the fidelity is not the best measurement, and the L1 norm or the L2 norm will be a better measurement for the similarity of both. Finally, once that we have encoded information and we have implemented the dynamics corresponding to the black source, we obtain a state that will have encoded the solution into the state that has the first spin linear state. Basically, we would like to retrieve this information. So just to do this process, we do it as follows. So the idea is that once that we have evolved our system, we'll make use of an ancillary Hamiltonian just for the measurement, that we have a dependency of K, and that we'll have sigma x interaction for the second spin, together with the position operator, and evolving the system according to this Hamiltonian, we'll have a dependency of this observable, such as if we measure the expected value in time, it will correspond to the Fourier transformation of the function that we want to retrieve, depending on k, which is the parameter that we have in the Hamiltonian. So by changing this parameter in the Hamiltonian, we can perform several measurements of the Fourier transform, and then we can retrieve the information applying the discrete time Fourier transform that will allow us to retrieve the original function from discrete measurements of the transform. And the most complicated part here is that we have to measure this coherence. It is not trivial, and it requires a more sophisticated protocol that can be achieved by evolving the system with this interaction Hamiltonian of the two spins, and then calculating the expected value with certain value of the parameter. It cannot even seen, but its implementation, it is not quite trivial. And eventually, some of the points, the next steps. So the first one is we still need to explore the accuracy needed to retrieve information with according to the Fourier transform and how to retrieve the inverse Fourier transform. Then write the article that I hope that you can see soon in archive. You can read because I'm going to read about it. So thank you all for your attention, and I hope that you enjoy. Do you have any questions, please? Yeah.
No. So we were discussing about that already, right? But it seems that the dynamics that this equation introduces is not so. I mean, it induces some little change to the state, right? So you start from some initial state in this functional degrees of freedom, and after the dynamics, right?
Yeah.
The wave function didn't change too much.
Well, in theory, the final state with respect to the final state has an overlap of 0.6. theoretical. It is not
Okay,
a great change. And basically, the main dynamics is given by the Hamiltonian that has the sigma y for the first speed. This driving is the main change in the dynamics.
all right, I see. But this 0.6 is because, okay, so you introduce it, I mean, you force a little bit, right, to get, you force a situation in which,
Yes,
because we were exploring other situations in which, I mean, that change was not so high, right?
yeah, that's because of the nature of the financial problem, because if this is the initial condition, the graph is going to do two things due to the form of the partial differential equation. So you have a drift plus dispersive charge. So basically, it is going to move and it is going to be a squeeze in that way. So basically, the final state is going to be quite similar to the original one, at least that it is implemented for a really long time, or that you increase these terms by tuning the economical, the financial parameters. So typically, the financial parameters are quite small, especially in our times in which things as these are basically zero.
So then I wonder if there is a, okay, instead of simulating the whole dynamical equation, right, maybe you can write something like an effective model of this dynamical equation that only captures these little deviations, right? So this little, maybe could be more effective. I am on the I don't know.
Yeah, a good idea.
Probably the other, because it seems that the Scholes equation by itself doesn't produce a really big change, right?
No, it does not. Actually, in the first slide, I'm showing which is the dynamic in a manifold here. So basically, the dynamic is not quite strong. So it has a slight change across time, but yeah, unless that you apply really long time, or you have a really strong value of the parameters. For instance, this risk-free interest was quite large 20 years ago, but now it is irrelevant. So,
I see. So then, I mean, I want to play the role of the David Lawyer. So, I mean, this is not against very much involved in this work. So, I mean, someone could ask, okay, then as it's a very little change, I mean, why this is relevant? Why is still a quantum simulator for solving something which, in principle, leads to a very little effect, right?
But this is not the question, because this model has an analytical solution.
Even I mean, it has an analytical solution.
yeah.
So why I need a quantum simulator for this?
Well, the point here is trying to find ways of solving this kind of partial differential equations. So in this case, the Scholes one has an analytical equation, so we can compare the performance of the different techniques with the analytical solution and check how good they are.
Okay, because
So-
this could be something like a first step towards doing
Yeah.
something more complicated problem, right? So,
Yeah, when we add some more complex partial differential equation that make that they are not analytically solvable, we
so one interesting thing is that typically here you are dealing with continuous variables, right? And in that cases, I mean, the dimension of the system scales horribly, right? They scale very bad. So probably if your Scholes equation, I mean, I don't know what is the next step in complexity in financial models, right? It would be something probably more complicated than Scholes. I would say, I mean, you know more than me, right? But if everything is encoded in continuous variables, I mean, that scales horribly. It's really bad. Really difficult to compute these things, right? So probably, I mean, so what you mean is that you are doing something like first steps to encode these kind of financial models in a system, right? That could scale, right?
That's it.
Yeah.
So basically, the next dependence is that this volatility that is assumed to be constant among all the process depends on the position. So you will have a dependence on the position plus a dependence on the equation itself on the momentum. So it's going to be complicated to mix both terms.
Which is the advantage with respect to the digital approach?
Well, the advantage is that we are not forcing. We are trying to leverage the natural dynamics of a certain system. But at the moment, we have not seen an advantage because the solution, the accuracy of the solution is quite worse with respect to the digital solution.
It's not that it's worse, it's that it's not controllable.
Yeah. We don't have the techniques yet to implement this with accuracy enough because, for instance, the encoding into the harmonic wave functions only can be done for a few pop states. We want the accuracy to load the initial condition, we will need at least 40, but it's not something available today.
Yeah, but also for the digital, I mean, here you would have advantages, right? Because the digital case, I mean, to encode something continuous in the digital is, I mean, you have to truncate many things and do it several bits, or not?
Yeah, the point in the digital is that we have to create a grid of points, and with n qubits we have 2 power 2 to the n points. So while we keep the number of operation depending polynomially on the number of qubits, we will have certain advantage against classical techniques that have also a grid of 2 to the n points. And in this case, I don't know which will be the fair comparison against a classical method. Obviously, you cannot compare against the analytical solution because it is supposed that the analytical solution is something that exists for this particular case. But if we were using a similar technique in classical computation, I don't know which would be the fair comparison because we have fine difference technique, finite different techniques, or we have also the exponentiation of matrices to solve all these dynamics.
But for instance, for the case in which the volatility depends on time and position, here the trick that you were using for replacing that cosine, very complex Hamiltonian that you have there, by a very simple one that is time dependent and the accuracy is really, really good, can be extended to much more complicated systems. And in this case, one could expect much better results than the ones that we are showing here. Better in comparison. I mean, of course, it is an analog simulation. You can never control completely the accuracy of your algorithm. But the scaling here, we have two qubits. There's a digital one. We have at least 8 qubits.
Yeah, that's true.
8 to 10 qubits.
Yeah, but all the tricks that you have to perform are not easy at all.
Of course, you have to tailor the techniques for each problem. This is the bad thing, but also with the digital, it's exactly the same.
But for the digital, I guess that now there are more people investigating on the loading and the retrieval,
But for me, I have still a question because the retrieval of information is for me a little bit tricky. So if you're using the same technique for the retrieval than for the loading of information, yes, inverse. So just to put down the amplitude. How are you going to? Because if now someone asks you which is the price for certain x, how are you going to do it? So you have to do the integration until the same number of modes. Have you done it?
No, not yet. That's
okay. For me, this is the final.
That's the last part of the work.
Because I think that at the end, this will be good for you. Because the point is that you have oscillatory solutions. So when you do this, what you're actually doing is an integration over a certain range. And the positive and negative values are going to cancel themselves, between one and the other. And then the accuracy is going to be better. The accuracy, the numerical accuracy of the solution is going to be better than the fidelity that you're giving them.
Yeah, that's the point of defining a similarity measurement with respect to the...
No, but you are thinking, when you say, so you were thinking on comparing two wave functions. And I'm not telling you about comparing two-way functions. I'm telling you about comparing the results after the integration, if you want, or the integration of the results due to the fact that you can only recover the first components of the mode analysis of the first modes.
Yeah. The point here is that we are retrieving the Fourier transform, so we don't have the continuous function, so we have to evaluate it.
Yeah, but this is going to be this is not what you are going to. If I ask you, give me the price, you won't do it. You do what I tell you. So you will use the same technique to recover the price around certain points, and this corresponds to an integration. And as you have oscillations, the mean value probably is going to be better than the value that you have if you see the function itself with infinite precision, which is meaningless because at the end, if you have upload the initial state with certain precision, you have to retrieve the information with the same precision. Otherwise, it's meaningless.
Yeah, if you have the possibility to retrieve information. I still have to explore that question.
So, in the digital approach, which was the approximation you used to discretize the continuous variable? So it was something like this, not your opinion, the other one, right? The one that changes the bosonic modes by qubits, right?
Yeah.
Force Primavera, right? Is that, do you use that in that, or is it a different story?
We just discretize the numerator, find that difference.
Okay, so you put something like in a grid. Right?
Yeah. We discretize.
Yeah, in sorts of like in positions probably, right? So
Yeah.
okay, I see.
Any other question?
¿Qué?
Puedes mirar si te llega un correo mío.
Correo.
Yo apoyo multimedia para el Facebook que voy a leer. Te mando un enlace.
Ay, Dios.